You were born moving. Not in the poetic sense, not as a metaphor for becoming. In the specific, measurable, physical sense, the kind that can be charted, calculated, verified with instruments. The hospital where you were born was rotating. Earth turns once every 24 hours, and depending on the latitude of that room, that rotation was already carrying you through space at somewhere between 0 and 1,000 miles an hour. Not relative to anything you could see, relative to the planet's own axis. 1,000 miles per hour in the moment your lungs filled with air for the first time. The hospital was also orbiting. Earth's path around the sun is nearly circular. Nearly, not perfectly, but close enough that the planet maintains a consistent speed of roughly 67,000 miles an hour along that path. 29 kilometers every second. In the time it takes to read this sentence aloud, perhaps 8 seconds, Earth has moved roughly 230 kilometers in its orbit. It will move that same distance in the next 8 seconds, and the next. Every 8 seconds of your life since the moment you were born. Every 8 seconds since before the planet had life on it. And the sun, the center of that orbit, is not standing still. The sun orbits the center of the Milky Way galaxy at approximately 450,000 miles an hour. One full orbit takes somewhere between 225 and 250 million years, a span of time so large that when the sun was last in this exact position in its galactic orbit, the most recent mass extinction event that would eventually kill the non-avian dinosaurs was still 200 million years in the future. The dinosaurs hadn't existed yet. The earliest mammals were only just beginning to appear in the fossil record. And the Milky Way itself, the center of that orbit, is also moving. The entire galaxy is falling toward the Andromeda galaxy, toward the combined center of mass of a structure called the local group, at speeds exceeding 1,000,000 miles an hour in one direction, while also streaming toward an enormous gravitational concentration called the Great Attractor at another velocity in another direction. The motions compound. The numbers accumulate. All of this was true in the moment you were born. Every second of your life since, you have never, not once, been still. You have been traveling through space at combined velocities that would destroy any aircraft ever built. Not as a passenger, not as a traveler, but as something embedded in the motion of the universe itself, carried along whether you intended it or not. Tonight, we take that motion and make it intentional. If in the moment of your first breath, you had aimed outward, deliberately in a straight line toward the nearest galaxy, what would that journey look like? What would you pass through? What would the crossing cost? And how long, at any speed the universe allows, would it actually take? The answer contains at least 4 things most people get wrong before the question even properly begins. It begins not with the distance, but with the destination. With which galaxy is actually nearest to Earth? A question whose answer is not what almost anyone thinks. Not the galaxy everyone names. Not the one you're probably picturing right now. The universe is larger than the assumption you arrived with. But in one specific direction, it is also much smaller. If this is the kind of night you return to, a night of questions that open rather than close, subscribe. It helps this quiet universe keep growing. Let's begin where the question begins. The nearest galaxy is not Andromeda. The answer everyone gives, Most people answer this question the same way. Andromeda. They know this one. The famous neighbor. The large spiral galaxy, 2.5 million light-years from Earth, visible to the naked eye on clear dark nights as a faint oval smear of light just south of Cassiopeia and north of the Great Square of Pegasus. When conditions are right and you're far from city lights, Andromeda appears as a softened, elliptical glow about 3 times wider than the full moon, though far dimmer, far more diffuse, visible only as the eye adjusts and the sky darkens. For centuries, astronomers debated what it was. The debate was not minor. For most of human history, the question of whether objects like Andromeda were close nebulae within our own stellar system or distant island universes, entire galaxies comparable to the Milky Way, was genuinely unresolved. The technology to settle it didn't exist. Photographs showed a spiral structure of some kind, but a spiral could be a nearby nebula or something entirely different at a vast distance. And without a reliable way to measure its distance, both interpretations were defensible. The question was settled in 1923 when Edwin Hubble, working with the 100-inch Hooker telescope on Mount Wilson in California, resolved individual stars in Andromeda's disk, specifically a class of variable stars called Cepheids, whose pulsation period is directly related to their intrinsic brightness. By comparing how bright they appeared with how bright they actually were, Hubble calculated the distance. Not a few thousand light-years, not even 100,000. Nearly 1 million light-years, a number later refined to 2.5 million, but already, even at that early estimate, large enough to make Andromeda clearly a galaxy in its own right, a separate system, an island universe. The universe expanded that night. Not physically, cosmically. The mental model of what the universe was changed permanently when Hubble published those measurements. Before 1923, the universe, in most educated people's conception, was essentially the Milky Way, perhaps surrounded by some nearby structures. After 1923, it became clear that the Milky Way is one galaxy among many, and that the universe contains structures at scales that had been, until that moment, inconceivable. Andromeda became the symbol of that expansion. The galaxy you could point at and say, there is another one. There are more. Which is why it became the answer everyone gives. It's the first other galaxy most people learn about. It's the dramatic one, the famous one, the visible to the naked eye one. It feels like the right answer. It isn't. Not Andromeda. Not close to Andromeda. Not in the same order of magnitude. What's actually closer? The nearest galaxy to Earth is a name most people have never heard in this context. Not because the information is obscure, it's in every introductory astronomy course, but because Andromeda carries so much cultural weight that the correct answer tends to get crowded out. The Large Magellanic Cloud. 160,000 light-years from Earth. Not 2.5 million. 160,000. Roughly 15 times closer than Andromeda. Visible to the naked eye from the southern hemisphere, not as a faint smear requiring dark skies and careful attention, but as a bright, obvious, impossible-to-miss feature of the southern sky, several times the angular diameter of the full moon. Ancient Polynesian navigators used it for orientation on open ocean crossings. Ferdinand Magellan's crew, during the first circumnavigation of the Earth in 1519 and 1520, encountered the southern sky and documented the bright cloud they saw there, giving it the name that has persisted through 5 centuries. The indigenous peoples of the Southern Hemisphere have records and traditions surrounding it going back to the oldest oral histories. For all of that history, for all of those thousands of years of humans looking at it, naming it, navigating by it, nobody knew what it was. It looked like a detached piece of the Milky Way, a cloud that had wandered free, a permanent fixture of the southern sky that never moved relative to the stars around it, that resisted every attempt to explain it as ordinary cloud or nebula. There was something different about it. But the instruments to understand what didn't exist for most of human history. It's a galaxy. Containing approximately 10 billion stars, one for every star in our galaxy, roughly, though estimates vary. An irregular dwarf galaxy, not a neat spiral, not a smooth elliptical, but something between and beside both of those categories, distorted by billions of years of gravitational interaction with both the Milky Way and its companion, the small Magellanic Cloud. The irregularity is not a defect. It's the record of a relationship, of tidal forces and gravitational pulls working on the galaxy's structure across timescales that make the whole of human history look like a single afternoon. The small Magellanic Cloud orbits at roughly 200,000 light-years from Earth. Also visible to the naked eye. Also a satellite of the Milky Way, so closer than Andromeda by a factor of more than 10. Together, the LMC and SMC are connected by a structure called the Magellanic Stream, a ribbon of hydrogen gas that stretches 300 degrees across the sky, invisible to the eye but prominent in radio surveys, being pulled from the clouds by the Milky Way's gravity. This stream is the Milky Way's gravitational claim on its satellites, the slow extraction of material that has been happening for hundreds of millions of years and will continue until the process is complete. Here's what complete eventually means. In approximately 2.4 billion years, models predict the large Magellanic Cloud will collide directly with the Milky Way. The nearest galaxy to Earth, the destination this question is asking about, is not static. It is on a trajectory toward us. The crossing you're imagining from here to there will eventually, on cosmological timescales, reverse into a collision initiated from there to here. But before the LMC, there may be something even closer. The galaxy inside our galaxy. The Sagittarius Dwarf Elliptical Galaxy. Approximately 70,000 light-years from Earth. Found in 1994. Less than 30 years ago. One of the nearest galaxies to Earth. Close enough that at the speed of light, you could cross to it in 70,000 years, not 160,000. And we found it within living memory. Not because it was hidden in a distant corner of the sky, because it was hidden in the most obvious place imaginable. The Sagittarius Dwarf is embedded in the plane of the Milky Way. Its stars are not concentrated into a visible cloud you can point at from a dark field. They are scattered throughout the galactic structure, diffuse, blended with the background of our own galaxy's stars, chemically and kinematically distinct, but not visually separable without careful measurement. For all the centuries of astronomical observation, for all the systemic surveys of the sky, the Sagittarius Dwarf hid in the crowd. It took infrared surveys in the 1990s, wavelengths of light that pass through dust more easily than visible light. Surveys designed to map the galaxy's stellar populations more completely, to finally separate its stars from ours by their chemistry and motion and reveal what was there. We discovered it in 1994, 70,000 light-years away, closer than the LMC, one of our nearest galactic neighbors. Found recently enough that astronomers currently in their careers remember when it wasn't known. And here's what the discovery revealed. The Milky Way is eating it. The Sagittarius Dwarf has been orbiting our galaxy for billions of years, and with each pass through our gravitational domain, our galaxy strips stars from its outer regions. Not violently, not in any sense you would perceive as dramatic if you watched from outside. Slowly, over hundreds of millions of years per orbit. The stars that are stripped don't fall into the Milky Way in a clean stream. They distribute themselves along the dwarf's orbital path in a structure called the Sagittarius Stream, a vast, looping ribbon of stars that winds around the Milky Way multiple times, above and below the galactic disk, detectable only in specialized surveys that can separate its stellar population from the background by chemical composition. The stream is so large, so distributed, that some of its member stars are relatively near us, not in any sense of nearby that has everyday meaning. These are stars separated from us by thousands of light years. But in terms of which galaxy those stars were born in, which galactic system formed them from their original gas, some of the stars you can see from Earth tonight were not born in the Milky Way. They were born in the Sagittarius Dwarf Galaxy 2 to 4 billion years ago, when that galaxy was more intact. And then the Milky Way's gravity reached out over billions of years and absorbed them into our structure. They orbit in our galaxy now. They have for hundreds of millions of years. They look like ours. They aren't. Think of two rivers converging. The smaller river doesn't merge cleanly into the larger. At the confluence, it disperses, its water threading into the larger current over miles of mixing. Detectably different in temperature and sediment and chemistry for some distance downstream, eventually indistinguishable except by the most careful measurements. The smaller river is still identifiable far downstream, in one sense. The water is there. But the river as a coherent body has ended. The Sagittarius Dwarf is the smaller river. The Milky Way is the larger. The mixing has been happening for billions of years. The dwarf still has a recognizable core, the dense central region we call the Sagittarius Dwarf proper. But its outer stars have been absorbed, distributed, folded into the fabric of our own galaxy. The galaxy you're asking about visiting? In one direction, you may already be touching it. Not traveling through our galaxy and then encountering another galaxy, but already in a region where the populations are mixed, where the distinction between us and them is a matter of chemistry and orbital history rather than physical separation. Then there's one more complication. The galaxy we can't decide on. The Canis Major overdensity. Roughly 25,000 light-years from the galactic center, approximately 40,000 light-years from Earth, in the direction of the constellation Canis Major, a concentration of stars that doesn't quite fit the Milky Way's expected structural model. Too chemically distinct from the surrounding stellar population to be easily explained as part of the normal disk. When astronomers first cataloged it, It was notable enough to require explanation. Two explanations emerged. The first, it's the remnant of a dwarf galaxy, another small system being consumed by the Milky Way, even further along in the absorption process than the Sagittarius Dwarf. Its core perhaps already gone, its stars in the final stages of being integrated into our disk. Under this interpretation, Canis Major would be one of the closest galaxies to Earth, perhaps even the closest, at approximately 40,000 light-years, a fraction of the LMC's distance. The second explanation, it's not a separate galaxy at all, just a ring of stars, a density fluctuation created by perturbations in the Milky Way's own disk, by resonance effects from the galactic bar, by the disk's response to gravitational interactions with passing satellite galaxies. Under this interpretation, Canis Major is not an external object at all, just our galaxy's disk doing something irregular. No outside origin required. Both interpretations fit the data reasonably well. Both have been argued seriously in peer-reviewed literature. Both remain viable. The debate is ongoing, and the people who have studied this most carefully do not claim to have resolved it. This is the state of the question, one of the closest potential galaxies to Earth, and we can't yet agree on whether it qualifies as a galaxy at all. Here's what that means for the question you started with. Which galaxy is nearest? It depends on which object you're counting. If Canis Major is a separate galaxy, the answer is 40,000 light-years. If it's Sagittarius Dwarf, 70,000. If it's the LMC, the nearest system that no serious astronomer disputes as a distinct galaxy, 160,000. None of those numbers is 2.5 million. You've been imagining a destination 15 times farther than the closest one. You've been picturing Andromeda, when the nearest galaxy might be something that humans navigated by for thousands of years without knowing what it was, or something we found in 1994, or something we still can't fully define. You've been closer than you thought your entire life. But here's what even 160,000 light-years actually costs. And here's why the journey starts not at the distance to another galaxy, but at the distance to the edge of your own. The Milky Way has no edge you can cross. The disk is not the galaxy. Before the crossing begins, the question assumes something it shouldn't. It assumes you can leave the Milky Way, that there is a boundary, a threshold, a marker in space where you pass from inside the galaxy to outside it. That the journey to another galaxy begins when you point away from Earth and start moving. You cannot leave the Milky Way the way you leave a building. There is no wall, no door, no edge that registers as an edge. The Milky Way does not end. It fades, slowly, over distances so large that by the time the material has thinned enough to call the space genuinely intergalactic, you have already traveled further than most people imagine when they picture the galaxy's extent. Start with what most people picture when they think of the Milky Way, the disk. The visible band of stars crossing the night sky on dark evenings, the diffuse river of light from horizon to horizon. This is the galactic disk, roughly 100,000 light-years across and roughly 1,000 light-years thick at our position. Thicker in the central bulge, thinner toward the outer edges. It is enormous. 100,000 light-years is a distance light takes 100,000 years to cover. The photons arriving from the far side of the disk left before our species existed. before the oldest cave art, before the beginning of agriculture or language as we know them, before anything that is recognizable as modern human culture. They've been crossing the disk in a straight line for the entire duration of human history, and they only just arrived. But the disk is not the galaxy. It is one layer of a structure that extends far beyond it in every direction. Think of it this way. If you compress the Milky Way's disk to the size of a dinner plate, 30 centimeters across, the disk would be approximately the thickness of a playing card. Flat. Impossibly flat relative to its width. And you, standing inside it, are in the middle of that playing card, embedded in the material, unable to see over the edges, looking outward through the dense structure in every direction parallel to the plate, and looking into relative emptiness above and below. That's the disk. That's the part most people mean when they say the Milky Way. And it's the smallest of three structures that make up the galaxy. The dark matter shell. Surrounding the disk, above and below it, extending far beyond its edges in every direction, is the stellar halo. A roughly spherical distribution of stars, far older than most disk stars, formed in the first billion years after the Big Bang, when the universe was young and chaotic and galaxies were still assembling themselves from the primordial gas. These halo stars orbit on elongated, highly inclined paths that carry them thousands of light years above and below the disk, and back again, on orbital periods of hundreds of millions of years. Some of them are among the oldest objects in the observable universe, stellar fossils, nearly as old as time itself, still burning in orbits they've traced since before the Milky Way had its current shape. The stellar halo extends to roughly 300,000 light-years from the galactic center, 3 times the diameter of the visible disk. Enormous by any standard, and yet most of it is so sparse that it's essentially invisible to the eye, even on the darkest nights. At Voyager 1 speed, the fastest sustained outward velocity we've achieved, crossing the stellar halo takes approximately 5 billion years, slightly longer than the Earth has currently existed. In that time, the Sun would have exhausted its hydrogen fuel, expanded into a red giant large enough to engulf the inner planets, expelled its outer layers, and collapsed into a white dwarf. The Earth would be gone before you cleared the stellar halo. But the stellar halo is not the outer boundary either. Beyond the stellar halo, extending in every direction to distances between 500,000 and potentially 1 million or more light years from the galactic center, is the dark matter halo. And this is where the scale changes entirely. Dark matter is the name given to something that most people have heard of, but whose full implications are rarely absorbed. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way our instruments can currently detect directly. We cannot see it. We cannot image it. We cannot sample it. We know it exists because of what it does to the matter we can see. Here's the evidence that convinced astronomers it was real. In the 1970s, an astronomer named Vera Rubin was measuring the rotation speeds of stars in spiral galaxies, using the Doppler effect to calculate how fast stars at different distances from the galactic center were moving. What she expected to find was what you'd expect from Newtonian mechanics. Stars at the outer edges of the galaxy, where the concentrated mass of the disk is far behind them, should orbit more slowly than stars near the center, just as the outer planets of the solar system orbit more slowly than the inner ones. What she found was different. The rotation curves were flat. Stars at the outer edges of galaxies were moving just as fast as stars much closer to the center. Not somewhat fast, just as fast. The mass implied by the visible disk was not sufficient to account for that orbital speed. If only the visible stars, gas, and dust existed, those outer stars should have drifted outward and dispersed the galaxy over billions of years. They didn't. Something was holding them. Something massive, distributed in a spherical halo far beyond the visible disk, providing the gravitational grip that kept those outer stars in their orbits. Rubin's measurement was confirmed by other groups in other galaxies using other techniques. The conclusion was the same. Galaxies are surrounded by vast halos of invisible mass, dark matter. Not hypothetical, observationally required by the data. 85% of the Milky Way's total mass is in this invisible halo. The stars, the gas, the dust, everything visible is the remaining 15%. The galaxy you see when you look up is the minority component of the actual structure. The dark matter halo, which extends to perhaps 500,000 to 1 million light-years in every direction and contains most of the galaxy's gravitational influence, is the dominant structure. And you are inside it. Not near its edge. Inside it. Deep inside it. The nearest edge is hundreds of thousands of light-years away. Think of it this way. You've been standing in what you thought was a room. You could see the furniture, the walls, the floor, everything visible. What you didn't know, the room is inside a sphere, and that sphere extends for 500 miles in every direction, made of material that doesn't reflect light or cast shadows. You only know the sphere exists because your furniture behaves strangely, staying put when it should drift, orbiting too fast, held by gravity that the visible room alone cannot explain. You're inside the sphere. You've always been inside it. The edge is 500 miles away in every direction. That's the Milky Way. Not the disk. The whole thing. What leaving actually costs. Let's make this specific. Let's use real numbers. At Voyager 1's current speed, approximately 38,000 miles per hour, 17 kilometers per second, the fastest sustained velocity we have ever sent an object away from Earth. To cross the visible disk, the bright 100,000 light-year band, the part visible on dark nights, takes approximately 1.7 billion years. The Earth is 4.5 billion years old. The disk crossing alone would consume more than a third of Earth's entire history. Let that settle. One trip across the bright part of the galaxy takes more time than the Earth has existed, divided by 3. To clear the stellar halo, the sparse population of ancient stars orbiting above and below the disk, takes approximately 5 billion years, longer than Earth has existed, longer than the sun has burned. In that time, starting from today, the sun exhausts its fuel and our solar system ends. The crossing would outlast the solar system. To reach the outer boundary of the dark matter halo, to arrive at space genuinely between galaxies, where neither the Milky Way nor any other system dominates the local gravitational environments, takes something between 15 and 20 billion years at Voyager speed. The universe is currently 13.8 billion years old. To escape the Milky Way's gravitational influence at our best achieved speed would take longer than the universe has existed. There is no scenario at any velocity humans have achieved or currently have the engineering capacity to achieve where escaping the Milky Way is fast. It cannot be made fast by clever trajectory. It cannot be shortened by aiming more precisely. The time is set by physics and by the scale of the structure you're inside, and that scale is immovable. The Milky Way doesn't end. It dissolves. And at every speed we've reached, the dissolving takes geological time. Here's what nobody thinks about when they picture this journey. And here's where the problem begins, not at galactic scale, but at stellar scale. Not at the distance of other galaxies, but at the distance of the nearest star. The sun never lets go. The gravity that reaches. Before you cross the galaxy, before you pass through the stellar halo, before you reach the dark matter boundary, before any of that, there is a more immediate problem, one that begins not thousands of light years away, but in the immediate vicinity of your starting point. The sun. Gravity doesn't have a surface or a boundary. It extends mathematically to infinite distance, becoming weaker with distance, but never becoming zero. The sun's gravitational influence, while negligible at the distances of other stars, is not negligible at the scale of the solar system. Not even close. The solar system, properly understood, is not 8 planets and a few rocky belts and then empty space. It is the full extent of the sun's meaningful gravitational domain, and that domain is vast. Start with the immediate problem. To leave Earth, just to stop being pulled back toward the planet's surface, you need to be moving at 25,000 miles an hour. That's escape velocity from Earth. At 25,000 miles an hour, you're moving fast enough that gravity never fully wins. Your curved trajectory through space eventually bends outward rather than back down. You don't orbit. 25,000 miles an hour sounds fast. No aircraft comes close. The fastest fighter jet ever built, the SR-71 Blackbird, flew at roughly 2,200 miles per hour. Escape velocity is more than 11 times that. It is a speed that no conventional engine, no fuel-burning rocket, no current propulsion technology delivers continuously. Chemical rockets achieve it in bursts, engines burning at maximum power for a few minutes before the spacecraft coasts on the momentum they've built. You cleared Earth's gravity at 25,000 miles an hour. Now you're in space, but not in open space. You're at Earth's distance from the sun, and the sun's gravitational influence here is significantly larger than Earth's. The escape velocity from the sun, starting at Earth's orbital distance, is approximately 94,000 miles per hour, nearly 4 times the speed you used to leave Earth. The gravity well you've climbed out of is not behind you. You've only climbed out of the smallest well, Earth's. Now you're at the bottom of the next well, and the sun's well is much deeper. Voyager 1, launched in 1977, exceeded solar escape velocity, but not simply from the rocket that launched it. It used gravitational assists, a trajectory calculated to fly close to Jupiter, then Saturn, using those planets' enormous orbital momentum to accelerate the spacecraft through a kind of gravitational slingshot. The craft borrowed kinetic energy from the planet's motion and redirected it into its own velocity. Without Jupiter's assist, Voyager would not have escaped the solar system. Jupiter is the largest planet in our system. Its gravitational influence is enormous. And we needed all of it, just to push a car-sized spacecraft past solar escape velocity. The Oort Cloud, where the solar system actually ends. Here's what most people picture as the edge of the solar system: Neptune. The outermost planet, roughly 30 astronomical units from the Sun, 30 times the Earth-Sun distance. Beyond that, in most people's mental model, space. Open, empty interstellar space. The solar system is not 30 astronomical units across. It is closer to 200,000. The Oort Cloud. It begins somewhere between 2,000 and 5,000 astronomical units from the Sun, roughly 2 to 5 times the average distance of Neptune from the Sun, times 30, or equivalently, somewhere between 180 billion and 450 billion miles from where you started. It extends outward from there, in a roughly spherical distribution of icy bodies, comet nuclei, rocky icy planetesimals, to somewhere between 100,000 and 200,000 astronomical units, 1 to 2 light years. 1 light year is 5.88 trillion miles. The Oort Cloud extends to approximately 6 to 12 trillion miles from the Sun. These objects, billions of them, perhaps trillions, are the leftover debris of the solar system's formation. When the planets were assembling from the disk of gas and dust surrounding the young Sun roughly 4.5 billion years ago, the gravity of the giant planet scattered enormous numbers of smaller bodies outward. Some were ejected from the solar system entirely. Many ended up in the vast shell we call the Oort Cloud, their orbits stable at those distances from the Sun, their surfaces cold beyond imagining, their light from the Sun so faint it is indistinguishable from the light of other stars. On occasion, passing stars or the gravitational influence of the galactic disk disturbs these objects and sends them on new trajectories, inward toward the Sun and the inner planets. These become long-period comets, visitors from the outer solar system with orbital periods of hundreds to thousands of years, arriving from directions that have nothing to do with the plane of the planetary orbits, trailing tails of sublimating ice and dust across the inner solar system before swinging around the Sun and departing into the outer reaches again for centuries. Every long-period comet you've ever heard of, Hale-Bopp, Hyakutake, the great historical comets that appeared unexpectedly across cultures throughout recorded history, came from this structure. Each one is a message from the Oort Cloud, a piece of the outer solar system disturbed from its ancient orbit and sent inward. Now make this a unit of distance. If you compress the Earth-Sun distance to 1 centimeter, smaller than the fingernail on your thumb, Neptune is 40 centimeters away, just over a foot. The inner edge of the Oort Cloud is roughly a kilometer away on this scale. The outer edge, 6 to 12 kilometers. The entire planetary solar system that gets taught in schools, all 8 planets, the asteroid belt, the Kuiper belt, everything from Mercury to Neptune, occupies the innermost centimeter of a structure 6 to 12 kilometers across. The planets are not the solar system. They're the central cluster, the core. The solar system continues far beyond them in every direction. At Voyager 1 speed, reaching the inner edge of the Oort Cloud takes approximately 300 years. Not 300 light years, not 300,000 years. 300 years of travel at the fastest speed we've achieved to reach the beginning of the structure that forms the true outer boundary of the solar system. Reaching the outer edge, 2 light years from the Sun, takes somewhere between 14,000 and 28,000 years at that same speed. 14,000 to 28,000 years. That number is longer than all of recorded human history. Longer than the development of writing, agriculture, cities, mathematics, science, and every civilization that has appeared and vanished since the last ice age. Longer than all of it. And at the end of that crossing, you would still be inside the Sun's gravitational domain. What Voyager found at the actual edge, Here's a specific number that anchors the abstract. In August 2012, Voyager 1 crossed a boundary that had been theoretically understood, but never before directly measured, the heliopause. The point where the solar wind, the continuous stream of charged particles emanating from the sun, finally becomes too weak to push back against the interstellar medium. The point where the sun's direct material influence ends and the interstellar material begins. Voyager had been traveling since 1977, 35 years, at speeds achievable only through gravitational assists from the two largest planets in the solar system. And in 2012, it crossed into what astronomers call interstellar space, the region between stars, at a distance of approximately 121 astronomical units from the Sun, 11 billion miles. The data from that crossing confirms something scientists expected but had never directly observed. Outside the heliopause, the particle environment changes. The density and composition of particles around the spacecraft shifted. The magnetic field orientation changed. Cosmic rays increased, high-energy particles from outside the solar system that the heliosphere had been partially deflecting. Voyager is now the most distant human-made object from Earth. As of the time this script is being written, it is roughly 150 astronomical units from the Sun, roughly 14 billion miles. It has been traveling for more than 4 decades. And it has cleared the heliopause, but it has not left the solar system. It is not yet at the Oort Cloud. It's 150 AU out. The Oort Cloud begins between 2,000 and 5,000 AU. On the scale of the solar system as properly understood, Voyager 1, 46 years of travel, the gravitational momentum of Jupiter and Saturn, the fastest sustained outward trajectory we've achieved, is 1 to 2% of the way to the solar system's true boundary. The speed problem begins here. Before you reach the stars, before you cross the galaxy, before you enter intergalactic space. Just getting clear of the structure centered on our own star, the structure that begins at Earth and ends 2 light years away, is already a journey that outlasts any human civilization. The space between stars. 1 atom per cubic centimeter. Suppose the problem of speed has been set aside. Suppose you're traveling at the speed of light, which makes the Oort Cloud a 2-year crossing and the LMC a 160,000-year journey. What do you actually encounter between the stars? What fills the space that isn't stars? Most people imagine it as empty. Not just sparse, truly empty. A vacuum. A void. Nothing between the stars but darkness and distance. That model is not wrong so much as incomplete. The space between stars is filled with what astronomers call the interstellar medium, a diffuse distribution of gas and dust, varying wildly in density and temperature and composition across the galaxy, but nowhere entirely absent. The interstellar medium comes in several phases, like water in its different states. The coldest regions, molecular clouds, where hydrogen exists as molecules rather than atoms, reach temperatures as low as 10 Kelvin, only 10 degrees above absolute zero. These are dense by interstellar standards, up to 1 million molecules per cubic centimeter. They're the nurseries of stars. New suns form in these clouds when gravity collapses regions of gas into concentrations dense enough to ignite fusion. The warmest regions, the hot ionized medium, primarily created by supernova explosions blasting hot plasma into the surrounding space, reach temperatures of 1 million Kelvin or more. These regions are the least dense, perhaps a 10,000th of an atom per cubic centimeter. Nearly a perfect vacuum by any engineering standard, but still technically there. The middle phases, warm neutral gas, warm ionized gas, occupy most of the interstellar medium's volume and have densities of roughly 1 atom per cubic centimeter. 1 atom per cubic centimeter. 100 to 1,000,000 times less dense than the best vacuum achievable in a physics laboratory on Earth. 1,000,000,000,000 times less dense than the air you're breathing right now. Here's how to hold that number in your mind. The room you're in, let's say it's about 50 cubic meters. In the average interstellar medium, that room would contain approximately 50 hydrogen atoms. 50 atoms. Not 50 molecules, not 50 particles in some complex distribution. 50 individual hydrogen atoms rattling around in 50 cubic meters. Everything else is nothing. The air in this room contains roughly 10 to the 27th molecules, a number with 27 zeros. Divide that by 50. The interstellar medium is less dense than your room's air by a factor of approximately 2 times 10 to the 25th. A 2 followed by 25 zeros. You would travel through this for tens of thousands of light years, for the entire crossing of the disk, the stellar halo, the transition region, and the material around you would be, in any practical sense, nothing. Nothing with structure. Nothing with phases and temperatures and field lines and radiation. But nothing. The local bubble we're already in. Here's a specific fact about our immediate neighborhood that changes the scale of even this emptiness. Earth does not orbit the Sun in the average interstellar medium. It orbits in a region called the local bubble, a roughly spherical cavity approximately 300 light-years across, containing gas significantly less dense than the interstellar medium average, at temperatures significantly higher. The local bubble is a hot, sparse region of space, embedded in the surrounding denser interstellar medium. We know this bubble exists because of X-ray observations. The hot gas inside it emits diffuse X-rays detectable from satellites orbiting Earth. We know roughly its size and shape. We know it is bounded on most sides by denser clouds of the surrounding medium. What created the local bubble? Multiple supernova explosions within the past few million years. Massive stars that exhausted their fuel and exploded, blasting enormous quantities of energy into the surrounding medium, heating it, pushing it outward, creating an evacuated region in the surrounding gas. We don't know exactly which stars exploded, or exactly how many, or precisely when. But the evidence for the explosions is in the bubble itself. We live inside the remnant of ancient stellar deaths. The boundary of the local bubble, where the hot, sparse interior meets the surrounding denser medium, is between roughly 100 and 300 light-years away, depending on direction. At Voyager speed, reaching the boundary of the local bubble takes approximately 2 to 5 million years. At light speed, it takes roughly 100 to 300 years. Before you've meaningfully crossed the galaxy, before you've entered any of the more dramatic regions of the interstellar medium, you first cross the remnant of several supernova, an evacuated cavity in space. A hot bubble of ancient stellar violence that happens to contain our solar system. The temperature that has no temperature. Here's where the physics stops being intuitive. The interstellar medium in its hot phase, the regions heated by supernova and stellar radiation, has temperatures between 100,000 and several million Kelvin. 1,000,000 Kelvin. 6 times hotter than the surface of the Sun. Astronomically, undeniably hot. And yet, if you entered such a region, if you are somehow there, in this 1,000,000 Kelvin gas, you would not feel heat. Temperature at its physical foundation is a measure of the average kinetic energy of particles. A gas at 1,000,000 Kelvin contains particles moving extremely fast. But temperature is not heat in the everyday sense. Heat, the kind that warms you, burns you, transfers energy to your skin, requires contact, requires particles colliding with your surface and transferring their kinetic energy to you. It requires those collisions to happen at a rate that deposits energy faster than your body can radiate it away. In a gas, at 1 atom per 10,000 cubic centimeters, the collision rate is essentially zero. 1 particle per cubic meter, moving fast, carrying its full million Kelvin kinetic energy, might strike your skin once per year, once per decade. In between those collisions, nothing. No heat deposited. Your skin radiates its own thermal energy away faster than any particle could deliver it. A thermometer in that environment would not read 1,000,000 degrees. It would read close to absolute zero, its own temperature, since nearly no energy is being added to it. Imagine a room where a single bullet is fired every week. The bullet moves at supersonic speed. In any physical sense, it carries enormous kinetic energy. But you are not hot. You might be struck once in a decade. The room does not feel dangerous in any conventional way. The concept of warm barely applies. That is the hot interstellar medium. Technically at 1,000,000 Kelvin. Physically inert because there's almost nothing there to interact with. The cold is worse in a different way. The cosmic microwave background, the faint radiation left over from the Big Bang, fills all of space uniformly at 2.7 Kelvin, 3 degrees above absolute zero. In the absence of any nearby star, any nearby heat source, any radiation to warm you, this is the background temperature of the universe. Cold in an absolute sense. Cold in a sense that biology cannot survive. Cold in a sense that makes the concept of cold inadequate. Between the stars, the universe is this cold. Between the galaxies, it is this cold or colder in the absence of any star whatsoever. The galaxy fights back. You cannot see your own galaxy. Here's something that sounds obvious once stated, but changes how you think about the journey. We cannot see the Milky Way from outside. We are embedded in it. We live inside it, 2/3 of the way from the center to the outer edge of the disk, embedded in a minor arm called the local arm or Orion arm, surrounded by the disk material in every direction parallel to the galactic plane. Our view of our own galaxy is like trying to understand the floor plan of a building while standing inside one of the middle floors, surrounded by walls in every direction. We can see the galactic disk as the band of light crossing the night sky. The stars so numerous and so closely packed along that band that they blur into a diffuse glow. We can see that the band is thicker and brighter in some directions, toward the galactic center in Sagittarius, and thinner in others, toward the outer disk. We can infer the overall structure from these observations, from radio surveys that penetrate the dust, from measurements of stellar motion, from comparisons with galaxies we can actually see from outside. What we've assembled from this inference is this. The Milky Way is a barred spiral galaxy. At its center, instead of a simple point, is a bar, an elongated concentration of stars, roughly 27,000 light-years long, from which the spiral arms emerge. Those arms, 4 major ones, plus several minor arms and spurs, wind outward from the ends of the bar, carrying the bulk of the galaxy's star-forming gas, its hot young stars, its interstellar medium. We are in a minor arm. The local arm, a spur between the Sagittarius arm and the Perseus arm. not a major feature of the galaxy's structure. A lesser branch. A sidetrack. Our distance from the galactic center has been measured and remeasured over decades with improving precision. Current best estimates put us at roughly 26,000 light-years from the center, a number revised downward from earlier estimates as measurement techniques improved. We orbit that center at roughly 450,000 miles per hour, completing one full revolution approximately every 230 million years. The forbidden zone at the center. The trajectory from Earth toward the LMC doesn't pass through the galactic center. The LMC is located primarily below the galactic plane, in the southern sky, in a direction that takes you out of the disk rather than across it. But the galactic center is always relevant, because any path through the galaxy must be planned with knowledge of what the center contains. The galactic center harbors Sagittarius A star, 4.1 million solar masses. A supermassive black hole, the kind of object that makes the most massive star in the galaxy look like a dust particle in comparison. 4 million solar masses compressed to a region smaller than our solar system. Surrounding Sagittarius A star is the central molecular zone, a region approximately 1,000 light-years in radius around the galactic center. This region contains some of the most extreme environments in the galaxy. Dense molecular gas at temperatures ranging from 10 to thousands of Kelvin. Concentrations of hot young stars packed far more tightly than anywhere in the disk. Magnetic fields orders of magnitude stronger than those in our neighborhood. And intense radiation at X-ray and gamma-ray wavelengths pouring outward from the galactic center's energetic environment. Any trajectory through the central molecular zone would cross environments that would challenge any spacecraft, any shielding, any biology. The radiation environment near the galactic center, the flux of X-rays, cosmic rays, high-energy particles, is vastly more intense than in the quiet disk where Earth orbits. Your trajectory toward the LMC arcs around this. Out of the disk, above the galactic plane, through the stellar halo, into the region where the galaxy is thinning, not through the center. The center is behind you and to your left, a concentrated glow at 26,000 light-years, visible as the brightest part of the galactic band, but not directly in your path. The galaxy has thickness in time, not just space. Here's the dimension of the galaxy most people miss entirely. The galaxy is not just large in space. It's deep in time. The stars in the galaxy span a range of ages, from less than 1 million years old. Hot blue O-type stars so massive they'll exhaust their fuel within a few million years and explode, to stars more than 12 billion years old, formed in the galaxy's earliest period, when the universe was less than 2 billion years old. When you travel through the galactic disk on the way toward the LMC, you cross regions of different stellar age. The spiral arms, where you are now, contain young stars and active star formation. Moving outward toward the outer disk, the stellar populations age, more intermediate-age stars, less active nurseries, the gas thinning and star formation declining. Moving into the halo, the stars are older still, ancient, metal-poor, chemically distinct from disk stars, formed before the galaxy had enriched its interstellar medium with the heavy elements produced by dying stars. The galaxy is a record. Its structure is not just geometric, it's historical. The different regions of the Milky Way preserve different epochs of its formation and evolution. As you travel outward, you move not only through space, but through time, through the galaxy's history made physical in the chemistry and age and motion of its stars. This is what the galaxy actually is, not a backdrop you travel through. A structure that contains its entire history, written in the chemistry and motion of hundreds of billions of stars, across a region of space so large that crossing it requires timescales measured in billions of years. The galaxy coming toward you. The local group. You are not alone in intergalactic space. The Milky Way is not an island. It belongs to a structure called the local group, a gravitationally bound collection of galaxies sharing a common gravitational environment, holding together against the expansion of the universe around them. The local group spans roughly 10 million light-years in its longest dimension. It contains more than 50 individual galaxies, most of them small, dwarf galaxies, irregular systems, satellite galaxies orbiting the two dominant members. Some are smaller than the Sagittarius Dwarf, containing only a few million stars. Some are intermediate. The Triangulum Galaxy, the third largest member of the local group, contains roughly 50 billion stars. The two dominant galaxies in the local group are the Milky Way and Andromeda. Together, they account for the vast majority of the local group's total stellar mass. Andromeda is the larger of the two, roughly 1 trillion stars to the Milky Way's estimated 250 to 400 billion. Andromeda is also more massive in total. It carries more of the local group's luminous mass, and its dark matter halo may be comparable to or larger than the Milky Way's. The Milky Way and Andromeda are the twin centers of this system. The smaller members orbit them, or orbit the barycenter of the two in complex trajectories. The Magellanic clouds are satellites of the Milky Way. Most of the other dwarfs in the local group are satellites of one or the other. This structure, the local group, is gravitationally bound. It will not be pulled apart by the expansion of the universe. Within the local group, gravity wins. The galaxies will interact, merge, and ultimately form a single structure over cosmic time. Andromeda is moving toward you. Here's what makes this personal. Andromeda, the galaxy everyone names when asked for the nearest galaxy, the galaxy that is actually 15 times farther than the LNC, is moving, not stationary, not drifting, moving toward us. Andromeda is approaching the Milky Way at approximately 110 kilometers per second along the line connecting our two galaxies, about 245,000 miles per hour, measured along the axis of approach. That's the component of its velocity pointing directly at us. There may also be a transverse component, motion perpendicular to the line of sight, but the uncertainty in measuring transverse motion at 2.5 million light-years makes it difficult to determine with precision. At the current approach rate, the two galaxies are expected to begin their first interaction in approximately 4 to 5 billion years. 4 to 5 billion years. That's the remaining stable lifetime of the Sun. In roughly the same span of time that separates us from the merger, the Sun will exhaust its hydrogen fuel and begin its death sequence, expanding into a red giant, consuming the inner planets, expelling its outer layers, and collapsing into a white dwarf. The merger of the Milky Way and Andromeda will begin roughly when the solar system ends. This timing is not a coincidence in any meaningful sense. It's a coincidence in the sense that the numbers happen to be of the same order of magnitude, nothing more. But it makes the event feel less abstract. You can hold both processes in mind simultaneously. the expansion and death of the sun, and the arrival of another galaxy. Different scales, the same time frame. The first pass and what follows. When the two galaxies reach each other, when the outer halos first begin to overlap, the merger does not happen in a moment. Galaxy mergers are slow, complex, multi-billion-year processes. Here's what the models predict. The first pass, the two galaxies swing through each other, their dark matter halos interpenetrating, their stellar disks distorted by tidal forces. Stars don't collide. The distances between individual stars are so vast that even when two galaxies pass through each other, the probability of any two stars directly encountering is essentially zero. The ratio of star size to interstar distance is like two handfuls of sand thrown into a volume the size of Earth. The grains never touch. But the gravity does its work. The disks are distorted. Stars on the outer edges of each galaxy are flung into new orbits, some ejected entirely into intergalactic space as tidal tails. Long streams of stars stretching out from the disturbed galaxies in arcing ribbons that can extend for hundreds of thousands of light years. Observations of other merging galaxies, the antennae galaxies, the mice galaxies, show these tidal tails in detail, dramatic, curving structures of displaced stars, ghostly tendrils thrown outward by the violence of the gravitational interaction. After the first pass, the two galaxies orbit each other again, farther apart momentarily, then falling back together on a longer approach. The second pass is more destructive. The structure is more disrupted. Eventually, after multiple passes and hundreds of millions of years of interaction, the two systems lose enough orbital energy to each other that they settle into a merged configuration. The result is called Milky-Way, a roughly elliptical galaxy. The merger destroys the spiral arms, disperses the disk material, redistributes the stars into a roughly spherical distribution. Elliptical galaxies don't have arms. They don't have the flat disk. They're older-looking structures, smoother, less dramatic, with little active star formation, primarily composed of older stars. Where will Earth, or what remains of the solar system at that point, be during the merger? Current models suggest a range of outcomes. The solar system might be flung to the outer regions of Milky-Way by a close gravitational encounter during the merger. It might end up relatively close to the combined center if its orbit during the merger happens to carry it inward. It might be ejected entirely into intergalactic space as part of a tidal tail. The models don't have enough precision to say which. The outcome depends on specific parameters, the exact trajectory of the merger, the specific orbital positions of each system at first contact, that are too sensitive to small uncertainties to pin down. What's certain is that the sky would look entirely different. The band of the Milky Way that we navigate by, the familiar distribution of constellations, the positions of the nearest stars, all of it would be replaced by something unrecognizable. A sky filled with stars in a new distribution, reflecting the merged structure. Nearby, perhaps, a region of higher stellar density as the galactic centers coalesced. The night sky of Milky-Way, seen from inside it, would be brighter than our current sky by some amount that depends on where the solar system ended up in the merged structure. It would be beautiful. And nothing recognizable from our current map of the sky would be there to recognize it by. The crossing, nothing for millions of years. 1 atom per cubic meter. You've crossed the disk. You've moved through the stellar halo. You've transited the outer regions of the dark matter halo, where the density of anything, matter, radiation, anything detectable, drops to its minimum. You're in what astronomers call intergalactic space, the space between galaxies. It is not empty, but it is close to the closest thing to empty that the universe contains. The density of the intergalactic medium, the diffuse material filling the space between galaxy systems, is approximately 1 atom per cubic meter, not per cubic centimeter as in much of the interstellar medium, per cubic meter. 1,000,000 times less dense than the interstellar medium average. 1 cubic meter is approximately the volume of a large laundry basket. In that volume, in intergalactic space, 1 hydrogen atom. Everything else is vacuum. Not the limited vacuum of a physicist's chamber where trace amounts of residual gas remain. A vacuum more complete than anything we can produce on Earth. In your room, let's say it's 50 cubic meters. In intergalactic space, that room would contain approximately 50 hydrogen atoms. 50 atoms total. And you would travel through this for millions of years, through space so empty that no detector could register the passage through any kilometer-scale volume, through space that registers, to all practical purposes, as nothing. No stars. The nearest star during the intergalactic crossing would be millions of light years away, not visible as a point of light to the naked eye, not a source of warmth, not a reference point for navigation. The Milky Way behind you, the LMC ahead of you, both visible as extended patches of light. The Milky Way slowly shrinking, the LMC slowly growing, over millions of years of travel. No other feature, just the two. The cosmic web. But intergalactic space is not uniformly empty. At the largest scales, scales of hundreds of millions of light years, the universe has structure. A structure called the cosmic web. Galaxies are not distributed randomly through the universe. They cluster along filaments, vast, thread-like concentrations of dark matter and diffuse gas that span hundreds of millions of light years. Where filaments intersect, galaxy clusters form. Enormous concentrations of hundreds or thousands of galaxies, hot gas, and dark matter. The densest structures in the universe. Between the filaments are voids, regions of space tens to hundreds of millions of light years across that contain almost nothing. Not simply fewer galaxies, vastly fewer. A void might contain 1% of the average galactic density, sometimes less. The local group itself is situated in a modest filament, a structure within the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster. Laniakea spans roughly 500 million light years and contains approximately 100,000 galaxies, including the Milky Way. It is one supercluster among many in the observable universe. The WIM, the warm, hot intergalactic medium, fills much of the volume of these filaments. Temperatures between 100,000 and 10 million Kelvin. Densities between 10 and 100 atoms per cubic meter. The boundary between filament and void is not sharp. It's a gradient from the sparse but detectable filament gas to the nearly empty void gas. For much of the intergalactic crossing from the Milky Way to the LMC, You are passing through the material associated with the local group itself, a region slightly denser than open intergalactic space, held together by the combined gravity of the local group's galaxies. This is not dramatic material. It is still extraordinarily thin by any terrestrial standard, but it is distinct from the truly open space of the cosmic voids, the duration that changes everything. Here's the number the question is really asking about. The Large Magellanic Cloud is 160,000 light-years away. At the speed of light, the physical maximum, that is 160,000 years. 160,000 years ago, modern humans were expanding across the continents. Neanderthals still existed in Europe. The oldest cave art we know of was decades away from being made. No agricultural society existed anywhere. No city, no writing, no mathematics, no recorded history. That is how long ago the light you'd be traveling at left, if your departure were concurrent with the photons that are arriving at Earth right now from the LMC. 160,000 years. All of modern human civilization exists in a small fraction of that crossing time. At Voyager 1 speed, 38,000 miles per hour, the calculation is different by a factor of 28,000. 160,000 light-years at that speed requires approximately 2.8 billion years. Not of intergalactic space, of crossing just the distance between the Milky Way and the LMC. Before that, you spent additional billions of years escaping the galaxy. 2.8 billion years of this. Of 1 atom per cubic meter. Of the Milky Way slowly shrinking behind you and the LMC slowly growing ahead. Of no stars close enough to show visible change. Of no landmarks. Of the cosmic microwave background, filling all of space at 2.7 Kelvin, so cold the concept of cold barely describes it. Of moving, continuously, through nothing. At Voyager speed, you would leave Earth in 2024. You would arrive at the LMC in the year approximately 2,800,000,000,2024. In that time, the Sun will have completed its entire remaining stable life. Earth will be gone. The inner solar system will be gone. If anything survives in the outer solar system, if the cold, rocky material in the outer reaches persists through the Sun's red giant phase, it will have existed for billions of years in a different solar system from the one that launched you. And you'd arrive at the LMC, 160,000 light years from where you started. Some of it is already gone. The observable universe and its limit. Here is where the journey hits something that cannot be fixed by speed. The universe is expanding. Not just expanding, accelerating. The space between galaxies that are not gravitationally bound to each other is growing, and the rate at which it's growing is increasing. Every galaxy not gravitationally bound to the local group is moving away from us, not because it's traveling through space, but because the space between us and it is expanding, carrying the galaxy with it. At large enough distances, space expands faster than light can cross it. Not because anything violates special relativity locally. Space expansion is different from motion through space. But the effect is the same. At distances beyond a certain threshold, roughly 14 billion light-years, recession velocities exceed the speed of light, and light emitted toward us today will never reach us. This is the Hubble sphere. the boundary beyond which the universe is causally disconnected from us in an increasingly permanent way. But the observable universe, the sphere of space from which we can currently receive signals, extends to about 46 billion light-years. That seems contradictory. If the Hubble sphere is only 14 billion light-years, how can we see anything farther? Because the universe hasn't always been expanding at the current rate. Light emitted billions of years ago from regions that are now 46 billion light-years away was emitted when those regions were much closer, only a few billion light-years, and the expansion rate was different. That light spent billions of years crossing space that was expanding beneath it, but it made it. It arrived. We can see galaxies that formed when the universe was less than 1 billion years old. Whose light has been traveling for 13 billion years to reach us, and which now reside at distances of more than 40 billion light-years due to the expansion during that transit. We can see them. We cannot reach them. And over time, we will lose even the ability to see more of the universe as additional regions cross the cosmological horizon. The coincidence of being here now. Here's something that rarely gets stated directly. We live at a specific moment in the universe's history. Not the beginning. The universe is 13.8 billion years old, and the first stars formed within the first few 100 million years. Not near the end. The universe will continue for hundreds of billions or trillions of years or longer, depending on its ultimate fate. We live at a midpoint of sorts, early enough that the universe's stellar era is still ongoing, late enough that galaxies have had time to form and evolve into the structures we observe. This timing is significant in one specific way. We can still see most of the universe. The cosmic web is visible in all directions. Galaxy clusters are close enough to observe in detail. The observable universe spans 46 billion light-years and contains roughly 2 trillion galaxies. The night sky, if you had eyes sensitive to all wavelengths, not just visible light, would show structure in every direction, down to the faintest signals from the earliest galaxies. In 100 billion years, roughly 10 times the current age of the universe, this will no longer be true. Dark energy will have expanded space to the point where all galaxies not gravitationally bound to what is by then Milky will have crossed the cosmological horizon. The night sky of that era will contain only the stars of the merged local group. No other galaxies will be visible. The universe will appear, to any observer in that future era, to be far smaller than it actually is, because all evidence of the larger structure will have receded beyond observability. An observer in that future era who had no historical records would have no way of knowing that billions of other galaxies existed. The universe would look like a single population of stars in a void. Everything beyond the local group, 1 trillion galaxies, the entire cosmic web, would be invisible and unreachable, not because it ceased to exist, but because it moved beyond the horizon. We happen to be alive in the era when the universe is still visible, when you can look in any direction on a dark, clear night with a large enough telescope and see galaxies stretching to the observable horizon, when the cosmic web is accessible to our instruments. This is not a permanent condition of the universe. It is a temporary window, one that is slowly closing on timescales of tens of billions of years. The window for intergalactic travel, even theoretical, even at light speed, is similarly constrained. Some destinations are already unreachable at light speed, their recession velocity exceeding what any trajectory can compensate for. Others are reachable in principle, but would require departure times long before Earth existed. The window for reaching many specific galaxies opened at some point in cosmic history and is slowly, irreversibly closing. You were born in the window. That fact, the specific cosmological timing of your birth relative to the universe's expansion history, is not nothing. The answer, what you would actually travel through. Let's bring this back to the specific journey. You left Earth the moment you were born. You're traveling at the speed of light. What does the crossing look like from inside it? For the first few weeks, crossing the inner solar system, the sun shrinking from a disk to a bright point over a period of weeks, the inner planets visible as moving points of light, the asteroid belt, the outer planets, Jupiter, Saturn, Uranus, Neptune, passing as points of light at their respective distances, each taking seconds or minutes to reach. After 8 months, the heliopause, the boundary where the solar wind gives way to the interstellar medium, detectable by the change in particle environment, the density of solar wind particles drops to zero, replaced by the sparse material of interstellar space. You are now technically in interstellar space, the region between stars. The solar system continues beyond you in the Oort Cloud, but the sun's direct material influence has ended. After roughly 1 to 2 years, the outer Oort Cloud, the solar system's true gravitational edge, where cometary nuclei in barely stable orbits feel the tidal influence of the galaxy itself, competing with the sun's faint gravity. You pass through without noticing any specific boundary. The material is so sparse that no individual object is within any detectable distance. You cross a gradient, not a line. For the next 26,000 years, crossing from the sun's position to the region where the galactic disk thins at the disk halo boundary, aimed southward, out of the plane, the stellar density decreasing as you move away from the disk. The galactic band visible behind and beside you, the structure of the disk laid out from a changing perspective, the spiral arms becoming visible in profile as you gain altitude above the plane. For the next 100,000 years or so, the stellar halo, ancient stars widely spaced, globular clusters visible as compact bright patches on their elongated orbits. The disk of the Milky Way becoming more distinct in your rearward view, identifiable as a disc-shaped structure. The spiral structure glimpsed but not fully resolved. The central bulge a distinct bright concentration. For the remaining time, approaching the LMC, the density of everything falling toward its minimum. The Milky Way behind you growing smaller. The LMC ahead growing larger. At some point, after perhaps 100,000 years of travel, in the deepest void of the crossing, neither galaxy dominates your view equally. The Milky Way has shrunk to a small spiral visible in one direction. The LMC occupies an increasing fraction of your forward view. You are equidistant between two galaxies. And then, gradually, the LMC resolves. Its structure becomes apparent. Its central concentration of stars, its irregular shape, its active star-forming regions, particularly the Tarantula Nebula, the most luminous star-forming region in the local group, containing dozens of massive stars so luminous they would be visible to the naked eye from Earth if they were in our galaxy rather than the LMC. You arrive. Not at a single point, at a galaxy. A system with 10 billion stars, its own spiral structure barely formed, its own dynamics, its own history of interaction with the Milky Way. And behind you, 160,000 light-years away, is the galaxy you started in, seen now as it exists 160,000 years in the past, because that's how long the light takes to travel back to you. The Milky Way of 160,000 years ago. Before our species existed in its current form. A spiral galaxy, its structure familiar, its specific star positions reflecting a moment long before the first modern human drew breath. You've never seen it from outside before. No human has. No human-made instrument has. The only images we have of our own galaxy from outside are images of other galaxies that look like us. The Milky Way, seen from the LMC, would be the view we've always wanted and could never have. Our home from a sufficient distance to see it whole. You've never stopped. You were born moving. Not in the poetic sense. In the physical sense. The hospital, the room, the bed, all of it moving through space at speeds that would destroy any aircraft. 1,000 miles an hour from Earth's rotation alone. 67,000 from its orbit around the Sun. 450,000 from the Sun's path through the galaxy. And the galaxy itself falling towards something massive and unnamed at over 1,000,000 miles an hour. You arrived into this. You didn't choose it. Tonight has been an attempt to follow one thread of that motion to its end. To take what was always involuntary and ask what it looks like when you mean it, when you aim it, when you go. And what you find, following that thread, is not primarily a story about distance. The distance is real, 160,000 light-years to the LMC, 2.5 million to Andromeda, 46 billion to the observable horizon. But the distance is not the story. The story is what you learn about the structure of the universe by tracing your own position within it. You learn that the galaxy you thought was nearest isn't. That the real nearest galaxy is one human navigators used for thousands of years without knowing it. That one of our near galactic neighbors was found in 1994. That one of them may be so absorbed into our own structure that the boundary between us and it no longer cleanly exists. You learned that the Milky Way doesn't end, that it dissolves over hundreds of thousands of light years through structures visible and invisible, through a dark matter halo whose outer edge is farther than any speed we've achieved could reach in the age of the universe. You learned that the space between stars is not empty, that it has texture, temperature, history, a local bubble blown by ancient supernovae, phases of gas ranging from 10 Kelvin to 1,000,000 Kelvin, cosmic rays threading through it at relativistic speeds. You learned that galaxies are not islands, that the local group is a family, that Andromeda is approaching, that the merger is coming on timescales that place it at the end of the Sun's stable life. That the merger will produce Milkomeda, an elliptical galaxy neither of its parents, a new structure carrying all their stars in new orbits around a combined center. You learned that some of the universe is already gone, not destroyed, but receding faster than light, sealed behind an expanding horizon, invisible in principle even to instruments of arbitrary power. That we live in a temporary window of cosmic visibility, that the window is slowly closing. And you learn the specific answer to the question, at light speed, 160,000 years to the Large Magellanic Cloud, 30 times longer than all of recorded human civilization. At Voyager speed, approximately 2.8 billion years, plus the billions of years required to escape the galaxy first. At any speed humans have achieved, the journey time exceeds the remaining life of the Sun. The journey is not possible. Not in any human time frame. Not in any civilizational time frame. Not in any biological time frame. And yet you have been moving toward it, toward everything, since the moment you were born. The hospital moving, the Earth orbiting, the Sun sweeping around the galactic center, the galaxy falling toward Andromeda. All of it in motion. All of it aimed at something. The universe does not stand still while you think about it. It was moving before you arrived. It will be moving after you're gone. You were born moving. You've been moving every second since. The crossing to another galaxy may be impossible in a human life.